Hello, this video will be looking at DC machines and in particular problems with commutation. As we've learned before, commutation is the process where the commutator switches contact with the brush in order to maintain a DC voltage in the DC machine. Problems with commutation are divided into two, which are armature reaction and LDI/dt voltages. At the end of this video, you should be able to explain the concept of armature reaction in DC machines, explain the effects of armature reaction, describe the cause of LDI/dt voltages, and explain the solutions for armature reaction. A DC machine will contain two parts. The first is the stator, which is the stationary part of the machine, and the stator would normally contain field windings or permanent magnets. Most machines would not have permanent magnets as you see here, which is a north pole and a south pole. They would normally have field windings. Now field windings are windings that are wound on the core to produce the main magnetic field in the DC machine. And as you can see here, the windings are these circles that I'm drawing. In order to produce a magnetic field that goes from north and traveling to the other side of the pole, using your right hand rule, the current would have to flow out from the top and in at the bottom, and that would produce the magnetic field that's flowing to the right. And in order for the magnetic field to carry through to the other side, the current must also flow out on the top of the other side and in at the bottom. The second component required in a DC machine is the rotor, which is normally containing armature windings inside slots in the circular rotating part of the machine. So these slots would contain your armature windings. Putting these two components together, you'd get the full DC machine, which looks something like this. And as I mentioned before, the stator would produce the main magnetic field, which is shown by these red arrows. As we've discussed previously, the magnetic field would cross the air gap at the shortest possible path, and that would mean it will cross the air gap perpendicular to the pole surface. And as drawn in this figure, the magnetic field is balanced and symmetrical along the vertical line of the rotor, and this vertical line is what we call the magnetic neutral plane. So the magnetic neutral plane is a point where the magnetic field is symmetrical on both the left and the right side of the DC machine. And at the magnetic neutral plane, the coils on the neutral plane would have zero induced voltage in them because the magnetic field at that point is zero. And on the same note, due to the zero magnetic field at the magnetic neutral plane, there will be no induced voltage and no induced torque. When a load is connected to the DC motor, currents would start to flow in the armature windings. As shown in this figure here of the armature or the rotor, the X in the armature coil means the current is flowing in on the right side of the coils, while the dot on the left side means current is flowing out of the coils. And as we've learned, a current flowing in a coil would produce its own magnetic field. Hence, the armature current would now produce an armature magnetic field. And the direction of the armature magnetic field can be obtained from the right-hand rule. So using the right-hand rule, where the current is flowing in the armature coils, the magnetic field would flow in a clockwise direction, as I'm drawing here. And on the left side, where the armature current is flowing out of the coils, the magnetic field would flow in a counterclockwise direction. So when we put all together, in the DC machine there are now two different magnetic fields. The armature magnetic field due to the armature current, as shown by the green lines in this figure, and the main magnetic field due to the main of field currents or magnets, which is shown by these red arrows. Now, when we have two magnetic fields inside the machine, some interesting things would start to happen, and we can see this in the two areas of interest in this figure denoted as A and B. So as was mentioned just now, the armature winding would produce its own magnetic field, and using the right-hand rule, the magnetic field flows clockwise on the right side and anti-clockwise on the left side. So we mentioned two interesting locations on this machine, and we denote this as 2 points, A and B. At points A, shown at the top right location here, the magnetic field are all pointing in the same direction. Both the armature magnetic field, the green arrow, and the red arrow, which is the main magnetic field, they are both pointing in the same direction. This means the fields add up, and this also happens at the bottom left side. While at point B, which is on the top left, you find that the main magnetic field and the armature magnetic field are flowing in the opposite directions. This also happens at the bottom right side. When the fields are in opposite direction, the fields tend to subtract. Now, what does this cause? The original magnetic field, which was previously very symmetrical along the vertical axis, has some more closely put arrows or close magnetic fields or more magnetic fields on the top right and the bottom left due to the fields adding up, and more sparse or less magnetic fields on the bottom right and the top left. And what we find here is at points A, the magnetic field has added, causing it to be closer to each other, and at points B, there's less magnetic field, making it more far apart. This means the main magnetic field in the eye gap of the machine has been distorted due to the armature current, and this is what we call armature reaction. Armature reaction only happens when there is a load connected to the DC motor, whereby the armature current is not equal to 0. And as armature current increases, there will be more distortion in the magnetic field, and you get more armature reaction as the load or the armature current increases. So problems with commutation, we've looked at the first one, which is armature reaction. And armature reaction, as explained, is the distortion of the main magnetic field due to the armature current producing another magnetic field, which is called the armature magnetic field. And armature reaction only happens when there is a load connected to the DC machine. So what we're going to look at next are the effects of armature reaction. And there are two main effects, which is called the neutral plane shift and flux weakening. So the figure here shows a DC machine which has balanced magnetic field with the magnetic neutral plane on the vertical line. However, as mentioned before, armature reaction causes distortion of the main magnetic field in the DC machine due to the armature current, and this only happens when there is a load connected and armature current is not equal to 0. So the distortion in the magnetic field would mean the magnetic field is bunched up, or there's more magnetic field at the top on one side and the bottom of the other side, and there's less magnetic fields due to the subtraction of the magnetic fields on the other sides. This means the symmetrical point of the new magnetic field is now at this new neutral plane. Because as you can see here, the more magnetic fields on these two sides means that the symmetrical axis has been shifted to this new location, and this is what we call the new neutral plane, compared to the original neutral plane, which was on the vertical line. So the first effect of armature reaction is a neutral plane shift. And this neutral plane would have adverse effects on the DC machine because originally at the original neutral plane, we said that the induced voltage should be 0. But now that the new neutral plane has been shifted, the induced voltage at coils X and Y, which are now on the vertical axis, is no longer equal to 0. So imagine if you are having brushes that are commutating at the original neutral plane. The brushes are now short-circuiting commutator segments with voltage that is no longer 0, and this would mean arcing and sparking will occur during commutation. A normal DC machine without load connected would have a balanced magnetic field as shown in the figure here on the right, where everything is balanced on the left and right, and the vertical middle line is called the neutral plane. Now most machines operate near the saturation point of the BH curve, which is shown here in this point. And this is called the knee of the BH curve. Now what happens in armature reaction is there will be a distortion of this main magnetic field. And as you can see here, the distortion causes some areas to have more magnetic field while other areas have less magnetic field. So as mentioned previously, this is the effect of armature reaction, which is a distortion of the main magnetic field when there is a load connected and armature current is flowing. At points A of the DC machine, you can find that there's more magnetic field because the armature MMF adds to the pole MMF. But if we were to plot this on the BH curve, you would see that the increase in the MMF only causes a small increase in the flux. Now, there's another point in the magnetic field of the DC machine when armature reaction happens, and this is shown as point B. At point B, we said that the fields are in the opposite directions, and so the armature MMF subtracts from the pole MMF. So if we were to plot this in a BH curve, the subtraction is to the left of the normal operating point. And if we were to see the decrease in the decrease in flux, it is shown here to be much larger than the increase in flux. So the next effect of armature reaction is there will be flux weakening because the decrease in flux is much larger than the increase in flux due to the shape of the BH curve. So in general, the overall effect is the average flux under the pole will be decreased due to the armature reaction. And as we have learned, the induced voltage in the DC machine is equal to K flux omega. Now, if this induced voltage is equal to a constant, then speed is inversely proportional to flux. And as flux decreases due to flux weakening, the speed of the machine would increase. And this increase in speed will keep on happening if the current IA, the armature current, keeps on increasing, because as IA increases, armature reaction or AR becomes worse and the flux reduces further, and the speed will keep on increasing in a motor. So what we have seen thus far is the first problem of commutation is armature reaction, which is the distortion of the main magnetic field due to armature current flowing. And armature current only flows when there is a load. And the effect of armature reaction is divided into two, which are neutral plane shift and flux weakening. And as we've seen before, the neutral plane shift causes arcing and sparking because commutation happens at a point where the induced voltage is no longer zero, and flux weakening causes the speed to increase because as flux decreases, the speed of the machine will keep on increasing. So what we're going to look at next is the second problem of commutation, which is the LDI/dt voltages. Now, what are LDI/dt voltages? These voltages occur in commutator segments that are being shorted by the brushes. So normally, if you can see here in this figure, A, B, C, and D are the commutator segments. Now, let's say the brush is in contact with segment A, and the brush would cause current to flow in, and let's say the current flowing in is 400 amperes. So what will happen is when the current flows into the brush and reach the commutator, there are two coils connected to the commutator. So the current would split 200 amperes to the left and another 200 amperes to the right. And this current on the right will then flow to the second coil connected to commutator B. Now, the machine is rotating or moving, and let's assume the direction of movement of the motor is to the left. So after a few seconds, the brush would then be in contact with the second commutator, which is commutator B. So initially the brush was at commutator A, but now the brush has moved to commutator B, and the same current is flowing in, which is 400 amperes. So what will happen now, the current that is initially flowing in this coil connected to commutator B initially was 200 amperes to the right, but due to the movement of the brush, the current is now to the left 200 amperes. So what happens is the current flow through the commutator segment has reversed from 200 amperes to the right. Now it is 200 amperes to the left. So the total change in current if you take to the right as positive, then 200 amperes minus negative 200 amperes, which is a total change in current in that coil of 400 amperes. And this reversal of current direction from right to left happens very quickly. So how fast does this happen actually? Now assume your motor is rotating at 800 RPMs and there are 50 commutator segments. The commutator segments, I repeat, are the points A, B, C, D shown in this figure. So to calculate the time taken for the brush to move from one commutator segment to another commutator segment, you have one revolution of 50 segments of commutators rotating at 800 revolutions per minute, and this will come out to be 1.5 milliseconds. What I'm trying to say is the brushes change from one commutator to another commutator in a very short time, which is 1.5 milliseconds. And within this short time, the reversal in current must go from one direction to another direction at a very, very fast duration. So if we were to calculate the average rate of change of current, di over dt, we had a change in current of 400 amperes in a short time of 1.5 milliseconds, and this comes out to be 267 kiloamperes per second. And if we were to multiply that di by dt with an inductance L, any small inductance, for example 1 millihenry, multiplied by 267 kiloamperes per second would cause a voltage of about 267 volts. Now this voltage is what we call the L di dt voltage. So the L di dt voltage only happens at commutator segments that are being shorted, and it creates a large voltage due to the inductance in the machine. And this large voltage can cause arcing and sparking in the brush that is commutating or shorting the commutator segments. So this is the second problem in the commutation of the DC machine. So as we mentioned, there are two problems in commutation. The first is armature reaction and the second is L di dt voltages. And most of these problems would create arcing and sparking in the machine, which can be dangerous if the machine is placed inside an explosive environment. So what we're going to look at next is what is the solution towards these problems in commutation. The first solution is by having interpoles. Now interpoles are small poles that are placed midway or halfway in between the two main poles. So I'm drawing here where the position of the interpoles would be. And what would happen is, normally in a normal DC machine, the neutral plane is this middle line, which is what we call the original neutral plane. However, we've mentioned that armature reaction will cause a distortion in the main magnetic field and the neutral plane would be shifted as shown here. So this new shifted line is the new neutral plane due to armature reaction. And what happens is the new neutral plane will cause the coils X and Y. X and Y initially had zero induced voltage when there is no armature reaction, AR. But with armature reaction, the induced voltage is no longer zero at coils X and Y. So what will happen? The job of the interpoles will be provided with current or supplied by current. And the interpoles would produce a flux. And the flux from the interpoles will cancel the voltages in the coils X and Y to make the induced voltage zero again. at the original neutral plane. So once the induced voltage goes back to zero, there will be no more sparking at the brushes. So the interpoles are to produce a flux that will cancel the voltages in the coils at the original neutral plane, and this will then overcome the neutral plane shift problem. The second solution to armature reaction is by having compensating windings. Now, before I explain compensating windings, let's look back at what happens in a DC machine. The main magnetic field are these red lines or red arrows shown, and when armature current flows in the coils, the armature current will produce an armature magnetic field, and according to the right-hand rule, on the right side, when the current is going into the armature windings, the armature magnetic field will flow in a clockwise direction. And on the left, where the armature current is flowing out of the coils, the armature magnetic field will flow in a counterclockwise direction. And this armature magnetic field causes a distortion to the main magnetic field, which is the cause of armature reaction. So the compensating windings are windings that are placed in the slots carved in the faces of the poles, parallel to the armature windings. So I'm drawing here these blue circles, and these blue circles are the compensating windings. So you'd have the compensating windings on the north side of the pole as well as on the south side of the pole. And the compensating windings will be given current opposite to the direction of the armature winding. So on the north side, where the armature winding current is going out, the compensating winding currents will go in, as I'm drawing here. And on the left side, where the armature current is going in, the compensating winding currents will flow out. Okay, so now we have currents flowing in the compensating windings. And the currents in the compensating windings would then produce its own magnetic field. So the field from the compensating windings will flow using the right-hand rule on the north pole as the compensating winding currents are going in. So the compensating magnetic flux, compensating winding magnetic flux is what I'm drawing now. As the current is going in, the compensating field winding, magnetic field will be in a clockwise direction. And on the south pole, where the compensating winding currents are going out, the magnetic field will be in a counterclockwise direction. So what we can see is the fields from the compensating winding totally cancels the armature field because they are in opposite directions. And the cancellation of the armature magnetic field by the compensating winding magnetic field eliminates the distortion of the main magnetic field and cancels armature reaction. So compensating windings are able to overcome both effects of armature reaction, which are neutral plane shift as well as flux weakening. So what we are left with after the cancellation of the armature magnetic field is a nice DC machine with only the main magnetic field in effect, and the neutral plane is back to its original position in the vertical line, and there's no more flux weakening because all the armature magnetic field has been cancelled by the compensating winding magnetic fields. So in conclusion, the problems of commutation are divided into two: armature reaction and LDIDT voltages, the effects of armature reaction is neutral plane shift and flux weakening. Now, both these effects of armature reaction can be solved by having compensating windings. But interpoles can only solve one of the effect, which is the neutral plane shift. Interpoles cannot solve the flux weakening problem. However, for LDIDT voltages, there are no solutions. So unfortunately, compensating windings can only solve armature reaction problem but is unable to solve the LDIDT voltage problems. So I hope this video has been able to help you understand armature reaction, the effects of armature reaction, what are LDIDT voltages, and the solution towards armature reaction. Thank you. Bye-bye.